6.2 geometric sequence. Before I get too far, I have put AS instead of GS in a couple of spots incorrectly. Didn't get around to fixing it, but not the end of the world. So, our learning intention, how to find the nth term of a geometric sequence and how to model geometric sequences real life scenario. Our success criteria, I can identify the pattern in a geometric sequence and find the rule for the nth value. I can identify the initial term and the common difference, in this case, common ratio, in a real-time application question. So, what are geometric sequences? A geometric sequence is a sequence of numbers that has a starting term and is formed by multiplying the preceding term by a constant called the common ratio, denoted by R. So in this instance, we've got our geometric sequence. In arithmetic, we had a string of numbers. We used 3, 5, 7, 9, 11, and they all had a difference of 2. So going from the first term to the second to the third was a common difference of 2. In arithmetic, we're talking plus and minus. In geometric, we are now talking division and multiplication. So instead of having the common difference, we're now talking a common ratio. So for example, the geometric sequence 1, 2, 4, 8, 16, 32 has a common ratio of 2. As you can see, to get from 1 to 2, you times it by 2, 2 to 4, times it by 2, 4 to 8, times it by 2. And the geometric sequence of 120, 60, 30, 15, etc. has a common ratio of 0.5. So to get from that to that, you divide it by 2 or you times it by a half. When we're talking common ratios, we normally multiply rather than divide. A way to find R, the common ratio, is either to recognise it by inspection or to divide any term by the one before it. So let's go up to this one here. We know that this is our term 1 and this one is our term 2. So the common ratio formula is term 2 divided by term 1. In this case is 2 on 1 equals 2. That's for the first one. For the second one, second sequence, we do it again. T2 divided by T1 gives us 60 on 120 equals a half. So all you need to generate a geometric sequence is the first term A, so we still need to utilise that first term A, and the common ratio. Graphing geometric sequences. So we saw that we could graph an arithmetic sequence, and that is linear, it is a straight line. In the case of a geometric sequence, it's got a bit of a curve. It looks a lot like, more like a logarithmic type or an exponential type graph. So when R is greater than 1, the graph is in the shape of a curve with increasing values. So if our R is a whole number, it's increasing. Geometric sequences are not clearly linear, since the graph of a sequence is not a straight line. Again, self-explanatory. Graphing geometric sequences. When R is between 0 and 1, so we don't have, or we can have a negative R value, but when it's between 0 and 1, the graph of is the shape of a curve with decreasing values. So you can see as n increases, the t of n decreases. That means that we've got, 0.1, 0.2 as an R value, or 1/3, or 3/8. You don't have a whole number. It lies somewhere between 0 and 1. The rule for the nth term of a geometric sequence. So we're using this same table as what we had yesterday, or similar concept, to the arithmetic sequences. 1, 2, 4, 8, 16. So our R is 2. We're going to call that, keep that as 2. And T1, T2, T3 to T5, and my R is equal to R. My initial term is in the sequence is 1, and in the second column, my initial term is A. So I'm going to keep these, remember, I'm going to keep these as A and 1. And I'm also going to keep my common ratio as 2 and R for the purpose of showing you or demonstrating what's going on here. If anyone is following from their textbook, it is on page 264. There's a table there. Moving on to our second term. We're going to take our first term, then we're going to multiply it by our R value. T1 equals A times R. Now, I'm not finding the solution to this. I'm not simplifying anything as yet. Onto my T3 value is my previous term, which is 1 times 2. Then I'm going to times it by another 2. So suddenly I've got 1 and I've got 2 2's. And in the second column, my that's T2, my T3 is my previous solution, and multiply that by another R, which gives me A times R squared. T4, I'm multiplying by the previous term and by another R, which gives me 1, 2, 3 R's in this case, or 3 2's, and completing the same with the alphanumerical. Oops, shouldn't have deleted that. Let's get rid of that. Why is my pencil not working? There we go. So it's A times R multiplied by another R gives me 1, 2, 3 R's, A times R cubed. T5, still following the same suit, so I've got 1 times 2 times 2 times 2, so I've got my 3 2's there. Multiplied by another 2 gives me 1 times 2 to the 4. And my T5 with my alphanumeric, R times R, and then multiplying by another R gives me A by R to the 4. Now I've kept the T20 just to show you that when I have the n value to 2, I have a little imaginary 1 in there. So I have my power to 1. When I have my n value of 3, I have my power, or my indice to the power of 2. When I have 4, it's the R value is to the power of 3, and 5 is to 4. In the second column, I'm going to just jump down to the 5s. As you can see again, my T5, my n value is 5, my R value is 4. So my formula for this, when I have T of n, it's equal to A times R to the n minus 1, so 1 less than what that n value is. The rule for the nth term, T of n, is a geometric sequence. Of a geometric sequence is Tn equals A R to the n minus 1, where T1 equals A, the first term, and R is the common ratio. We'll go through a couple of examples. Blue's a better colour. If the can't even talk tonight. If the first 6 terms of a geometric sequence are 2, 6, 18, 54, 162, 486, state the value of the 8th and the 15th term in the sequence. So this is work example 3 on page 264 of your text. Let's start with this. My A value. My A value is my initial term, which is this guy here. So my A is equal to 2. And my R, using the formula, T2 over T1 gives me 6 on 2. That's equal to 3. That was the easy bit. I've identified my A, or my first value, and my first term, and I've identified my common ratio. Moving on to part 2, use the formula T of n equals ARn to the minus 1 to find T8 and T15. So all we do is we substitute substitute 8 into n for the first one. T of 8 equals A times R to the 8 minus 1, which is 2 times 3 to the 8 take 1 is 7, which is, I'm going to cheat a little bit here, 4374. I'm going to pop that in the calculator. And T15, doing exactly the same thing, A times R to the 15 minus 1, substitute the values in, 2 by 3 to the 14, pretty big number, is 9565938. Now step 3 just says write the answer, which we've already done there and there again. Work example number 4 on page 265 of your text. A population of rabbits is seen to increase so that each month the population is 111% the size of the previous month. If the population at the end of the first month was 20 rabbits, how many rabbits will be in the population in 2 years? All right, 3 key things we need to pull out of this. First of all, what's my A value? My A value is how many rabbits I started with. So A is 20. It doesn't give me a sequence of numbers, but it does give me 2 other figures. My R value in this instance is 111% because that's what it's increasing by. So it's about pulling this key information out of the example or out of the question to be able to then or solve the equation. So I have a 111% as my R value, but I am going to be working in decimals, not in percentages. So if I divide that by 100, I get 1.11, which is my R value. And my N value is 2 years, but we're talking months. So I need to multiply that by 12 to get my 24 months. Now, describe the sequence using T of n equals AR to the n minus 1. So what this means is just sub in values. So if anything says to you, describe the sequence, just chuck in the values. So T of 24 is equal to 20 by 1.11 to the power of 24 take 1. We'll simplify that. And that is your sequence. Now we just need to solve it. So plug all of that into the calculator and you end up with 220.525 rabbits. Now, we need to round to the nearest whole number. Because this is 5 or above, this number goes up. So we're talking approximately 221 rabbits because, you can't have half a rabbit. All right. So that's pretty much the explanation of geometric sequencing. I will be following this with 6.3, which is first order recurrence relations, which is sort of a combination of both arithmetic and geometric.